Questions in a variety of topics. I've been at Washington University for 3 decades now. I'm a geophysicist. Most of my research deals actually with seismology and earthquakes, but I'm also very involved with education and outreach. I've co-authored 35 textbooks now at a K through graduate school level, including national elementary school, middle school, programs, high school chemistry, physics, earth science books with Pearson Prentice Hall, and was one of the lead authors of the National Next Generation Science Standards that 45 states have adopted. So, and I will try to avoid the doom and gloom too much, which is very easy to do when we talk about this topic. That's why I had a slightly positive view here, and I will talk about new trends in science education at a K-12 level at the end. Let me start with this question: what is there? Why do we need to save the Earth? All right. Some of you may know the New York Times author Nicholas Kristof, who writes an article at the start of each year about why that past year was the best year in human history. So here it is in January 6th of 2018, why 2017 was the best year in human history. And then why the next year, why 2018 was the best year in human history. And this year, well, you know, why 2019 was the best year. And his premise is, when I was born, more than half the world lived in abject poverty, more than half the world was illiterate, and now fewer than 10% of the world lives in abject poverty, and fewer than 15% is illiterate. Every day, another 300,000 people get access to electricity and fresh water, and another 200,000 are pulled out of abject poverty. So, aren't things going in a good direction? What's the problem here? Well, the problem is, to make this happen requires squeezing out of our planet resources at an unsustainable rate. Basically, we're at about a planet and a half's worth of resources that we pull every day, so we're borrowing against our students, our children's future. By doing that, the area of parking lots in the United States, parking lots and roads put together, is now larger than the size of the state of Georgia. And the area of our towns and cities put together is now larger than the size of the state of California. And in fact, humans now control more than 50% of the planet's surface. And in fact, we use 40% of it at a global level to feed ourselves with our livestock and our crops. Actually, 50% in the US, we're at a very temperate climate. And the other 60% includes the Himalayas and Antarctica and the Sahara Desert, places that aren't so easy to grow food. So we're already kind of maxed out on our planet. This is an interesting graph, and sorry it's small here, but it's a plot of how we use land in the United States. Everything from corn syrup and golf courses here, and rural housing and railroads and forests. Where's the land that we're not actually actively manipulating? This is it. National parks, federal wilderness, and state parks. We now control the whole rest of that land. And to give you a scale of it, if you take all the world's land masses and you broke them up by humans, or what we eat, and I'll put our pets in there as well, and all other wild land mammals, humans are 36% of the total weight of land mammals. What we eat is 60%, and all wild animals now are just 4%. That's the degree to which we control our planet. Very powerful study by the World Wildlife Fund of 16,000 separate populations of vertebrate animals. So these are mammals, reptiles, amphibians, birds, and fish. Show that from 1970 to 2012, more than half, 58% of all vertebrate animals were killed or died. What happened to them? Well, we ate them or killed them for sport. And then there's habitat change, habitat loss, climate change, human-driven invasive species, and pollution. This is obviously not sustainable. What happens in the next 40 years? Are they all gone? Now, some animals have done fine. Rats and pigeons are thriving in our cities. Obviously, there are lots of cattle. They don't end so well, but there are many on the planet. But everything else is having a really rough time. Every person in the United States now requires over 50,000 pounds. That's more than 25 metric tons of stuff pulled out of the ground to make our laptops and our tables and our buildings and everything in our industrial world. To the point that human-driven erosion is now 6 times all natural causes together. Take glaciers and wind and rain and rivers. We're 6 times that. If you were to write a geology textbook now, the first 20 chapters would all be about you, and then the last few chapters would be about everything else. Because we are by far, by an order of magnitude, the largest agent of geologic change on the planet. And that's hard for many people to figure out because I'm one person, well, how powerful am I? Right, what can I do? But taken together, with 7.6 billion of us, it's massive. I mean, if for dinner today, every one of us decided to have a fish for dinner, right? A trout or something, you know, that's 7.5 billion fish that would have to be killed for that one meal. And at that level, you realize sort of the staggering proportions. To give you some scale of this, the Mississippi River Basin drains the entire interior of North America. The inexorable erosion of the mountains, tearing down, you know, the backs of the Rockies and the Appalachians, carrying, on average, about 300 million tons of sediment, rock, and dumping it into the Gulf of Mexico every year. That's about 5 freight trains from New York to Los Angeles filled with rock, okay? We pull out of the ground 8,000 million, 8 billion tons of rock a year, more than an order of magnitude more. And of course, the biggest impact is our insatiable addiction to energy and power on literally a planetary scale. We use energy at a rate of 20 terawatts. Just to give you a sense, our whole planet, all planets, lose space, heat out to space over time. We were mostly molten early on in our solar system's history, and we have cooled off, and we lose heat to the universe at a rate of about 47 terawatts. So in other words, if you were to somehow capture every joule of energy leaving the planet, that would only give you about twice what we actually consume. Every bit of heat from every volcano coming out of the ground, right? So we have a problem in that we see numbers like that, and they just sort of go right over our head, right? Does that mean anything to you, 20 terawatts? All right, well, how about 20 trillion joules per second? Does that help? No. Well, supposedly Newton was inspired by a falling apple. Well, it turns out 1 joule of energy is about the amount of energy it takes to lift a small apple 1 meter, right? So gravitational potential energy, if you remember this from your high school physics class, is mgh, mass times gravity times height. So if you have an object that's 1/10 of a kilogram, which is about a small apple, and you lift it 1 meter in a gravitational field that's around 10, 9.8 meters per second squared, 0.1 times 1 times 10 is 1. So I happen to have a small apple in my pocket. That is 1 joule of energy. Okay. And if I do it every second, that's a watt. So now I have a scale for what 1 watt is. And I see a couple other fruit, blackberries or apples or whatever. If you have your apple, if you want to join in, this is sort of audience participation. We'll do it Jack LaLanne style. Dates me a little bit, but 1 and 2 and 3. Okay, my arm is already getting tired. And if all of us doing this continuously would be enough to power 1 20-watt light bulb. Right? Now, how much would we actually have to do to provide our energy? Well, that's 20 trillion apples lifted up a meter every second. And if you take that and you divide it by the number of people in the world, that's every person in the world bench pressing 580 pounds every second, 24 hours a day, 365 days a year. Now, it turns out there are a few guys in the world who can do this. They do it once, they have a spotter to make sure they don't kill themselves, and then they're done. Okay? But for our energy, it would be 508 every second. Every man, woman, and child continuously. But actually what I told you isn't true, because you're not everyone, you're Americans. We have 4.5% of the world's population, but we use 20% of the world's energy. So for us, it's about 2,000 pounds we would need to lift every second, 24 hours a day. And there isn't anything. It doesn't exist. And we've already seen earlier what the consequences of this is. Because, up until now, most of this energy has come from burning fossil fuels, which is millions of years of stored sunbeams, basically. It's the photosynthesis of tens and hundreds of millions of years concentrated into coal and petroleum. And when you release that, the greenhouse gases cause the average temperature on Earth's surface to increase. So here's the last century. 2016 was actually the highest. Last year was the second highest. 2016 was high because that was an El Nino year. And when you have an El Nino, you actually borrow heat out of the Pacific Ocean. And when you have a La Nina, you put it back in, basically. And so, but it's interesting. Someone asked me, well, how about St. Louis? Now, I came to St. Louis 30 years ago, so I'm actually from New Jersey, East Coast. But back when I was born, the temperature in St. Louis was noticeably cooler. And if you plot out the average mean temperature, annual temperature for St. Louis since 1960, the temperature's gone up 4.5 degrees Fahrenheit. That's a rate of 7.5 degrees per century, right? That's not sustainable. It's not very long before that temperature is pretty much through the roof. Right, and as was mentioned, we understand the connection, the greenhouse gas effect of that, and so the temperature has been increasing rapidly, and of course the IPCC reports give you a range depending upon the choices that we make in the future. But I will say, the last IPCC report, the AR5 report, came out back in 2013. Or has data from 2013. We have been awaiting the next IPCC report. It is due out next year, and there are some early results that have leaked out, and they're not good. Basically, they show that the possible increase in temperatures at the high end have been significantly underestimated. So our chance of having even higher temperatures by the end of this century are even greater. Most people are aware of that, whether or not they admit to it or not. What many people are not aware of, though, is how uniquely rapid that rate of increase is. Here's the last 1,700 years. And here's the medieval warm period, which actually wasn't a global phenomenon. It was really concentrated in sort of the northern hemisphere. And here's the Little Ice Age, which was a global phenomenon, about 0.5 degrees Celsius globally. And this is what's happened since then. And of course, this was when this figure was made, and this is 2016. So you get a sense of how rapidly this is going up. And if you look at a smooth plot for the last 12,000 years, the whole last interglacial, and I'm sort of not, I could talk more about sort of the mechanism of climate, but basically we're locked in a pattern now due to Jupiter's effect on our orbit, which causes our Earth's elliptical orbit to get stretched out and become more eccentric with a period of about 100,000 years. In a pattern of having a long ice age, 90 to 100,000 years, and a fairly brief, what we call interglacial, warm period in between. This interglacial has been unusually long, largely because of human agriculture, which removed carbon from forests and put it in the atmosphere. And so we've actually created a longer, stable, last 10,000 years that has allowed civilization to continue. The earliest signs of civilization actually go back 130,000 years ago. And as was mentioned, modern humans, Homo sapiens, evolved about 300,000 years ago. These people were the same as us. They had the same brains. Only that interglacial was very, very brief. And it went right back into the Ice Age, and agriculture, cultures fell apart. And we went through another 100,000-year spell of basically hunter-gatherers until this last warming. And we reached our peak at about 7,000 years ago, and we were slowly going to head off into the next Ice Age. And then we kicked ourselves out of it with the greenhouse gases. This plot was made in 1990, and here's 2016. So while we've seen warmer temperatures, I mean, you go back to the time of the dinosaurs, there were no ice caps. The world was much warmer. Oceans were flooded. As was pointed out, the sea level was actually 400 feet lower during the last ice age than it is now. When all that ice melted, the sea level went up 400 feet. And to give you a scale of how what shorelines can do with 400 feet, if you go down to St. Louis and you go down to the arch and you look at the elevation marker right where the river goes by the arch, that's 400 feet above sea level. So if you lift the sea level up 400 feet, the coastline can move 1,000 miles inland. That's how flat most continents are. So we have some factors that have been helping us out. The ocean is one of them. 93% of all the heat that's been generated has gone into the oceans. The ocean is a huge sponge, a reservoir of heat. This particular study shows a slice through the Atlantic and the Pacific in the 1950s, 60s, 70s, 80s, 90s, and aughts. And you can see how this heat is being pumped into the ocean, which has kept our surface much cooler than it otherwise would have been. But the ocean goes through a circulation of about 800 to 1,000 years, so that's going to start coming back up at some point. Even if we were to stop all carbon release now, our descendants, hundreds of years from now, are going to feel the effects of our heating. And actually, we've benefited because the water that's coming up from the deep ocean in places went down during the Little Ice Age and is unusually cold. So it actually has been absorbing even more heat than usual. So this is helping out, but there's a limited amount of time. Also, both of the previous presentations talked about the social impact of this. And there have been quantified studies for a while now showing the change of climate and its effect on, in particular, conflict and warfare. The system isn't all that complicated. Crops are designed, they evolve to grow at certain temperatures, at certain climates. And if you change those climates, your crops fail. So the result of climate change is a loss of food. And when people are hungry, they are more apt to move to other places where there are already other people who don't want them there, and to undergo conflict. So this concept of climate change affecting interactions has been well documented. Here was a very impactful study that came out a couple of years that looked at local violence in East Africa, civil war across all of sub-Saharan Africa, and global conflicts across all tropical regions. And in every single case, when the temperature goes up, the number of conflicts goes up. So temperature goes up and people fight. Increased temperatures also correlate positively with domestic violence, with incidences of rape and crime, and even a decreased performance of students on tests. So we don't deal well when the temperature goes up. Another thing that happens, of course, when you increase the temperature is you melt the ice, as was mentioned. We fortunately have NASA satellites that can document exactly the mass loss of glaciers. And you can see this for Greenland. We're not only, are we losing, in this case, 250 billion tons of ice per year, but that the rate is steepening. So in other words, the rate of loss is increasing each year. We're now up between Greenland and Antarctica together, 500 billion tons of ice melt every year now. And of course, the sea level goes up. Hurricane Sandy was the first hurricane that flooded the subways of New York City. And the sea level there is only 13 inches higher than what it was in the 1800s. But as the climate scientist Michael Mann said, imagine that you play basketball and you lift up the whole floor of the court 1 foot. You just get a whole lot more slam dunks. And Hurricane Sandy was a slam dunk, and we're just going to get a lot more of them. As you mentioned, hurricanes become more powerful as the temperature differences from regions increases. And as you then raise the sea level and the storm surges become greater, that frequency of flooding increases. We already have places where it's called sunny day flooding. There's no storm. It's just the high tide of the month, and so the whole town floods. We've had places in southern Florida that have been continuously flooded for 4 months. And there's a sort of unusual circumstance there. The Gulf Stream, as you know, takes warm water, brings it up the East Coast and up towards the North Sea. Well, there's so much fresh water flowing off of Greenland that it essentially is blocking the Gulf Stream. And so the Gulf Stream has backed up, so the East Coast of the US has this backed up warm water. The warm water is less dense and it's a little higher in elevation, so the place is just perpetually flooded now. You mentioned the flooding of New York, and you had a picture of it. And this is a little, it's a little snarky, but this is a map of New York, of what it would look like with 100-foot sea level rise. And so here's the Isle of Brooklyn, here's Carnegie Island, Columbia, here's the Isle of Jersey. And actually, this is Teaneck Island right there. My high school is right there. So it's some comfort that when New York City's all flooded, my high school will still be there. The reason they chose 100 feet was the last time there were more than 400 parts per million carbon dioxide in the atmosphere, sea levels were 75 to 100 feet higher. Now you might look at that and say, well, wait a minute. If there's all that, and by the way, we've shot right through 400, we're at 413, and it just goes up year after year. Why isn't New York City flooded? Well, if you've ever, in the kitchen, if you're heating up a pot of water, you have to give it a lot of energy to heat that water. That's a very unusual property of water. It takes 5 times as much energy to increase water 1 degree than the equivalent mass of rock or wood or anything. So, and of course, it takes an enormous amount of energy to melt ice. So we are benefiting from the
fact that it's going to take a while to melt all those glaciers. Centuries, millennia, we don't know exactly. There have been some catastrophic break-offs of parts of the glaciers. We had the Larsen B ice shelf in West Antarctica collapse in 3 weeks. This is an ice shelf that's the size of a U.S. state. Okay, it's Rhode Island, it's the smallest state, but it's still a state. But 3 weeks, and it was gone, just disintegrated, it floated out to sea. So we don't know when this will end, but this is where the system wants to go, basically, at 400. But of course, as you pointed out, if we continue business as usual, we're up into 1,000 or maybe even 2,000 parts per million. And of course, the big issue in all of this is the human population. We wouldn't be having any of these discussions if our population level was the way it had been for 300,000 years. When I was born, right, I'm old, but I'm not that old, the world's population had just hit 3 billion people. It's now more than double that in my life. My father saw the world's population quadruple. And in fact, the population is going up so fast that 8% of every Homo sapiens that has ever walked on the planet is alive today. Okay? And because most humans died as children, more than 20%, maybe as much as 25% of all adult Homo sapiens that have ever existed are alive today. That's a function both of how new we are as a species on our planet, but also how ridiculously fast our population is going. We add another billion every 14 years now. Okay? In just today, there will be another 200,000 plus people added to the planet. I mean, that number is staggering. So that's a little doom and gloom, but here's the good news from my view, and that is, up until this point, and it's a long story that I won't get into. It goes back to a report in 1893 called the Committee of 10 report chaired by the president of Harvard University, Charles Eliot, and 9 other university presidents who said colleges need standards, so let's set some standards for middle school and high school. And they set the high school curriculum to be a year each of biology, chemistry, and physics. And at that point, geology, you showed a picture of plate tectonics there. Plate tectonics wasn't figured out until 1967. And Hubble didn't take a telescope and discover galaxies until 1929. So in 1893, astronomy was entirely left out of middle school and high school, and some physical geography went into middle school. Well, over the next 125 years, Earth science, geology, became an active field of research, and very important, dealing with Earth systems and climate and all that, but it's never been in the high school curriculum. Most Americans are asked to vote on these sorts of issues, and they know nothing about it. And so finally, there's a new set of standards